All right. All right, cool. All right, guys. So, yet again, I promised you a lecture and I didn't upload it. And the reason is that we're starting new material, and I felt like the chances of you guys actually watching the lecture before this lecture were kind of low, especially because you had a quiz that you were working on. So you're probably going to be pretty distracted and weren't going to watch the lecture, which means you're going to sitting in this lecture being lost because I've been ahead of you. So I'm going to backfill that lecture where I think it's appropriate. You'll always get, the amount of lectures that you're due. It just may fall in a different place, just for strategy's sake. That being said, everyone should have turned in their quiz to Nick at the beginning of class. If you haven't already, then you need to right now. You had a full 24 hours to do the quiz. I fully expected everyone has got the really good grade on it. I didn't obviously put any restrictions on how you worked on it, whether you worked together or whatever. I truly hope that you guys at least did the problems IRL instead of just asking ChatGPT to do it. If you did it, well, one thing is it may be wrong, and Nick can attest to that. Sometimes ChatGPT is wrong. One thing you have to appreciate about LLMs is that they're probabilistic models. So that means that there's some probability that they're going to spit out a bad answer. And in fact, for basic math, they're highly erroneous because what they're doing, right, is they are sourcing all of their data from the internet. And for really basic math, which Calc 2 is considered basic, there's a lot of bad Calc 2 out on the internet. There's a lot of stuff that people have written up that is wrong. And ChatGPT has no way of discerning whether it's right or wrong. And in fact, there are agencies that are employing lots of people to go through and annotate mathematics that are spit out by LLMs, by large language models, because of that very fact. That either it spits out stuff that's incomprehensible or it's just plain wrong and it has to be filtered. So I highly recommend that you don't use ChatGPT to do your math homework or your math quizzes. You may have gotten it right, you may have gotten it wrong. But what you definitely did, if you did use ChatGPT, is ensure that you don't understand it. So you will have to actually do this stuff on your own at some point in an exam situation. And if you work together and you collaborated, I feel a lot better about that. There's more learning going on in earnest in that situation. If you just typed it into ChatGPT and wrote down the first thing it spit out, then chances are you don't understand how to do it, and that's not going to do you any good. But I didn't put any restrictions on it because there's no point. I can't prevent you guys from using ChatGPT or whatever.
So I had a question about the quiz itself. The first two questions were very obvious in the notes, or like something very similar to it. But the third question didn't look very familiar.
Yeah, it was a new problem. That's why it was extra credit.
I think I got it right, but I wasn't sure. But it was like, oh, these two I just instantly recognized. It's like a variation of something else I've already seen.
Yes.
The other one I was like, I was staring like a deer with the headlights on.
Right. Yeah. The key to that one, if I recall, is to do a ratio test, or no, a root test or something. I can't remember, but
it's absolutely
I had ratio. It's factorial, so it's probably ratio.
Yeah. Okay. Right. I couldn't remember what it was. So yeah, one of the two, and it falls out pretty naturally, if I recall. But I'll write up solutions to the quiz now that everyone's, or I'll post the solutions to the quiz now that everyone's got it, and you can check it out. So, but I really hope that was an easy win for everybody. I know everyone probably could use a little bit of some cushion in their grades. So I hope that you use the opportunity to learn and also to get a good grade and make me and Nick's lives easier when we go to grade those quizzes together. It's a lot easier when you guys get everything right. So, all right, let's get to the stuff. Math. So much math. All right, we're in 9.7, and the topic du jour is power series. Why is this shaking? Gotta lock the wheels. maybe. Right. So in some sense, you already know what power series are, or you've been working with things that are like power series. But there is a slight kind of tweak to your perspective when you're looking at power series. So let's get the definitions out of the way. So what is a power series? We say a power series centered at x equals 0 is a series of the form the sum from n equals 0 to infinity of some coefficients, c sub n, so these are functions of n, times x to the n. So it looks like a geometric series, except you have this extra component, which is the coefficients. And so now the coefficients are going to be changing the way this thing behaves to some extent. There's also an additional definition, which is the power series that's centered at x equals a. So instead of x equals 0, and really all power series can just be subsumed under this definition. Same idea, except now we're looking at x minus a to the n. So really this captures everything, because we could let a equal 0 and we get back to the beginning. So I mean, a power series doesn't look like all that much. I mean, it looks very familiar or straightforward in some sense, but as we'll see, there's an interplay between the coefficients and our x here that can cause various things to happen. But let's start with the most obvious example, which is the geometric series. So we know this guy now pretty well, and we know it as the geometric series, but we can also think of it as a power series where all the coefficients are 1. So we're thinking about it differently. So think of the geometric series as a power series where all the coefficients are set to 1. So that's one slight tweak of our thinking. We're now going to kind of strip this of its identity. We're not thinking about it as the geometric series. We're just thinking of it as one particular power series. And we know how this thing works. We know what it converges to. So we're yet again going to kind of tweak our perspective on this thing. So we know that a geometric series is convergent if the absolute value of the ratio is less than 1, right? So for me in order for me to write this down, it's implied that this is true. But here's the tweak to our understanding. We know this expression is true. That's great. But from a power series perspective, we can think of the partial sums of this guy as approximations of this guy. So this is some function of x that I may be interested in. And in practical applications, sometimes you have functions whose derivatives or integrals are ugly, and you'd like to approximate it with something simpler, namely some sort of polynomial would be great. And what this connection between the geometric series as a power series and this function gives us is a whole slew of different polynomials that approximate this function. So if I look at the partial sums of this guy, so in this case, I'm going to look up to from k equals 0 up to n. So now some finite instead of infinite limit of x to the k. This is a polynomial, right? If we looked at it, it'd be 1 plus x squared all the way up to xn. This is a polynomial that is not exactly this, but it's pretty close to this. And the more terms we have in this polynomial, the better the approximation. So we can think of this as p sub n of x, a polynomial of the nth degree of x, and we can say that this is generally the case, that the polynomial approximates the function, assuming that, again, our x is between 1 and -1, strictly. So it's a slightly different perspective, but a more practical perspective. Like I said, this is just a polynomial. If I need to take its derivatives, it's just a bunch of power rules. It's easy to take a derivative of that. Taking the derivative of this, however, is a little bit more complicated, right? And if you think about it computationally, as in you're putting this into a computer, computing this derivative and then evaluating at different values is might be more computationally intensive than computing derivatives of a polynomial and calculating or evaluating at different values. So, this is one place where the math that you're learning here actually does have practical import. So it's just a slight tweak on our perspective, thinking about power series. Let's look at another example. So here we are looking at the sum from n equals 0 to infinity. And I'm going to write it like this: negative x minus 2 over 2. Just going to use a lot of brackets here. And all of that's to the nth power. So this thing is weird. It doesn't look exactly like anything we've seen before. It kind of looks like a geometric series. If it is the geometric series, which, I mean, any of these we can kind of think of as sort of mutant geometric series. It's an alternating one, since we have a negative here. Alternating geometric series, which we know can be absolutely convergent, assuming we have the right limitations on the ratio. So what are those limitations here, right? So if this is our ratio, everything that's inside of there, then we need the absolute value of that to be strictly less than 1. Which, we could simplify. The negative will go away. So we know that this alternating geometric series converges absolutely, provided this is true, right? So that's what I'm saying. This thing converges absolutely given this. Now that's great, but this isn't quite immediate. So what are the x values for which this is true? I need to do some manipulation on this inequality to figure out what the x values are. And while it may seem sort of like what's the point, what we're doing here ultimately relates to power series in general, and what we're going to find by manipulating this inequality is what we call the radius of convergence. So we'll define that more formally and look at it more in other examples. But here you're just sort of saying, hey, I know this is some sort of weird mutant alternating geometric series. What constraints do I have to impose on the ratio in order to get convergence, absolute convergence? This is the constraint. Let's figure out what it means for x specifically, right? Not just this function of x. So we're going to take that inequality, and anytime you have an absolute value less than something, you can always rewrite it like this. Drop the absolute value bars and write it as a compound inequality. So I'm just making, +1 and -1, flanking it on either side. And then we can solve this compound inequality, right? Multiply by 2. And then add 2. So we know we have absolute convergence for x between 0 and 4, strictly. But because this thing is a sort of mutant series, we still need to, or we're going to need to consider more than just this interval of absolute convergence. We need to also consider the endpoints. We could potentially have convergence at the endpoints as well. We know when we just had a regular old geometric series that the endpoints gave us something that was not convergent. But when we're dealing with these power series, sometimes the endpoints will come into play. So for instance, if I plugged in 4 into this guy, at x equals 4, this guy looks like 4 minus 2, which is 2, divided by 2 is 1. So it just looks like this, which we know is divergent. And if we plugged in 0 into that thing, we would get minus 1. So we just end up with the sum of 1, which we also know is divergent. So in other words, we check the endpoints, and we're going to have to do this every time with any sort of general power series. And we found out that they gave us divergent series at the endpoints. So this is the only interval of convergence. And we would call this for a power series, we'll call this the radius of convergence. Okay, so let's look at some more power series, and we'll see how we can use a ratio test to help us find the radii of convergences for each individual series. And then we'll define everything appropriately. So we're going to look at a number of examples here. In each case, what we're trying to do is find the largest interval for which our series, which is a function or dependent upon x, will converge. That's the goal. All right, so our first example is this guy. Okay, so now we've got something that's definitely not a geometric series. The previous example really was an alternating geometric series, but in this case, we've got something that is not. And remember, we're thinking of this as a power series. So, this is equal to Cn xn And so the coefficients, which are a function of n, in this case, that's everything you see here, right? That's your Cn. And so when the Cn is something non-trivial, right, it's not just set to a constant, then the series is going to change its behavior. And at that point, we no longer call this a geometric series, we just call it a general power series. So a geometric series is just a special case. So that's our Cn, just so you can start thinking about it that way. These are the coefficients as a function of n, and the x to the n is just this guy. So we know this is a power series that's centered at 0. That's the language that we want to use. And what we want to do is find the radius of convergence. And it sounds like a fancy thing to say, but it really is just the largest interval for which x will produce a convergent power series. So what we're going to do is use the ratio test. We know if this is convergent, if absolutely convergent, then it should satisfy the ratio test, right? So what does the ratio test say? It says we look at the limit as n goes to infinity of the absolute value. I'm going to drop the alternating component because we know we're taking an absolute value, so it's just going to go away anyways. And what do? We look at x, n plus 1 over n plus 1 over x to the n over n. So we're kind of doing this in reverse. We're saying, I want to figure out where this converges. I'm not trying to find out if it's convergent. I'm trying to find out where it could be convergent, right? Because we have this x here, it's like a dial. And we can change that dial in order to generate a convergent series. So it's still a slightly different perspective. We're not trying to assess its convergence. We're trying to find out what do we have to set the dial to in order to get convergence. So we're using the ratio test as as a way of figuring out what the range of the dial is, because we know that this has to be satisfied in order to generate a convergent series. So again, we're not trying to figure out if it's convergent. We're trying to find out where it could be convergent. It's a different thing conceptually. So we simplify this, we'll end up with just x. We'll end up with the n will come up to the top, n plus 1 on the bottom, and then we'll have an absolute value of x, right? X to the n plus 1 over x to the n will simplify to x, but the absolute value bars don't disappear because we don't know if x is positive or negative. All right, so we're taking a limit as n goes to infinity. The x doesn't depend upon n, so it's just a constant. You could think of this as the coefficient of the leading term in the numerator if you want. But we know what this will converge to. This term here will just go to 1. So that will just leave us with the absolute value of x. And in each of these cases, we are going to impose, based on our understanding of geometric series, that whatever the ratio is, which is just sort of generating the ratio for our power series, we know that this must be strictly less than 1. So in every case, we're going to assess this limit, get something, whatever it may be, and say it must be strictly less than 1. Okay, but we may have to do more work downstream of that. Here, we're sort of done. This tells us that we definitely have absolute convergence for x between -1 and +1. But just as I did before, we still have to test the endpoints. It's not sufficient to just say this. We know this is true. We have absolute convergence, but we may have additional convergence on the boundaries. And the radius of convergence is not limited to absolute convergence. We want to relax the constraint and say, where is it convergent, not just absolutely convergent? This is definitely the biggest interval for which it's absolutely convergent, but we may have something that's still convergent at the endpoint. So what happens at x equals 1? We plug that back into the series, right? So again, now the alternating component comes back into play because we don't care about absolute convergence anymore. And if I do that, I end up with this, right? The x term is just 1, so it goes away, and I get this guy. And what do we know about that guy? Anyone?
It's alternating P series.
Okay. What, be more specific, Ian.
So because P is 1, it converges conditionally, pretty sure.
Good. Right.
Yeah.
It converges conditionally, and that's all that we care about here. So this is an alternating harmonic, to be even more specific, right? When P equals 1, it's a harmonic. And we know that this is convergent, right? It's conditionally convergent, but I don't care about those distinctions right now. I just know this is convergent. Okay. So that means that x equals 1 has to be included in my radius of convergence. We also need to check -1. And if we plug in -1, then we are, I'll write it out explicitly. We'll have a -1 to the n, and then we'll have another -1 to the n, and that's all over n. And so these two alternating terms, they are the same sign at the same time, so they're going to cancel each other out, right? They'll either both be negative or both be positive. In either case, you'll always end up with something strictly positive. So now we have the series 1 over n. What do we know about that guy?
It's harmonic and it diverges.
It's divergent, right? So alternating harmonic, convergent, plain Jane harmonic, divergent. So that means our radius of convergence must exclude -1, but include 1. I think you guys, yeah, you can see the bottom of the board. So my radius of convergence, which I'm going to start abbreviating ROC. I don't have to keep writing it. The radius of convergence is -1 strict x less than or equal to +1. So again, our objective with these problems is not to assess convergence, but to figure out where it could be convergent. And the biggest interval for which it's convergent is the ROC. All right. We'll keep on doing more examples. So right now, what we've seen is that the ROC could be the entire interval for which it's absolutely convergent plus one of the endpoints. It could have been both, it could have been one, it could have been none. We've seen none before. When it's just a geometric series, we don't include the endpoints. With this guy, we included one of the endpoints. So here we're looking at the sum, n equals 1 to infinity, -1 to the n minus 1, x to the 2n minus 1, all over 2n minus 1. Right, so we got a power series. It's centered at 0. It's alternating, and it's definitely nothing like a geometric. It doesn't, it's just like kind of like the last one we just saw. It has coefficients that depend upon n. They're not all constant, so it's definitely not a strict geometric. So let's find the ROC. So first we'll use the ratio test to find the radius of absolute convergence. So absolute value, x to the 2n plus 1 minus 1 over 2n plus 1 minus 1. over x to the 2n minus 1 over 2n minus 1. So you got to be careful when you're simplifying this. Be careful when you're plugging in the n plus 1, right? I put it in parentheses. You'll never go wrong by putting it in parentheses. And you got to be careful with your algebra here. So when we go to simplify this, if I look at the exponent here, I'm going to end up with a 2n plus 2 minus 1. So I'll end up with a 2n plus 1. And this one has a 2n minus 1. So they differ by how much? How many degrees do they differ by? How much bigger is 2n plus 1 from 2n minus 1?
2.
2. So when we go to simplify it, we're just going to end up with x squared. There's an absolute value bars around this, but x squared is strictly positive, so I can drop them. I'm going to move that over, but we'll still have some n stuff going on. So that just is the x's. What's going on with the n's? You're going to have a 2n plus 1 in the denominator and a 2n minus 1 in the numerator. And then we'll have an x squared. So when we take this limit, it's just like the last one. It's the ratio of the leading coefficients, which is this 2 over 2, which equals 1. So the limit of this is x squared. And yet again, we need to impose that this is strictly less than 1. For absolute convergence, that must be true. So what does that say? If x squared is strictly less than 1, then that says that x is between negative 1 and 1 in order for x squared to be less than 1, right? How can you see that? Remember, I could take a square root here. If I take a square root of a square, as you've learned in this class, that will tell you equivalently that the absolute value of x is less than 1, which gives us here. All right, so that's the radius of absolute convergence. Now we're going to relax the constraints and look at the endpoints. Could we have convergence at the endpoints? What happens at x equals 1? At x equals 1, we get this guy. What do we think about that? All we want to know is it convergent or divergent?
It looks like an alternating harmonic series. Looks
Good. Yeah, it's if we squint our eyes, it's an alternating harmonic, which means it's convergent, right? Now, how would you show that technically, right? Because it isn't a harmonic, it's something a little bit different, right? So the way we would show that is by using the alternating series test, right? So we know it's convergent by applying this. We can show it's strictly positive. We can show that it's non-increasing. And we can show that it goes to 0 as a sequence. So that's convergent by the AST. X equals -1. We plug that in. What's going to happen? Well, we already have a -1 to the n minus 1. Now we'll have a -1 to the 2n minus 1 all over 2n minus 1. So what does that do? If I combine the negative ones here, this is different from the last one. We're going to end up with -1 to the 3n minus 2. Okay, so I'm running out of board space, so I'm just going to do that all in one. And if we think about 3n minus 2, depending upon the n, well, here's the question. Can that produce both even and odd numbers? Will it always be even? Will it always be odd? Will it be both? 3n minus 2. Well, if you plug in 2, you'll get 6 minus 2, which is 4, which is even. Is there any way to get an odd out of it? If I plug in 3, I'll get 9 minus 2, which is 7, which is odd. So I can see that this thing is actually bouncing between evens and odds, which means that that -1 doesn't go away, which means that this is still, yet again, an alternating harmonic-ish series. It looks a lot like this. So, in fact, it's probably identical, or close to being identical up to a sign. So yet again, this is convergent by the AST. So that means our radius of convergence, the ROC, includes -1 and includes 1. So here we've seen that the previous one, we were only including one endpoint. Here we included both. So it could happen that both are included. So I'm just doing lots of examples because I think this is the best way to get a feel for this stuff. All right. So we're seeing different variations on the theme. So let's look at another one. X to the n over n factorial, n from 0 to infinity. And in case, I don't think I ever said it out loud, but in case you don't know, since we're starting at 0 here, that means that the very first term will have a 0 factorial. And by definition, because I never said it, 0 factorial is equal to 1. So in case that's confusing to you, that is just by fiat, right? By mandate, that is that is what that means. Right, so let's find the ROC for this guy. First, we're going to find the radius of absolute convergence by looking at the ratio test. N plus 1 over n plus 1 factorial over n factorial, absolute value. What are we going to get here? We're going to be looking at the limit as n goes to infinity. We have an n factorial that will come up to the top over an n plus 1 factorial. So that all that will survive when you simplify those guys is an n plus 1 in the denominator. And for the x's, we'll have only an x left over. So it'll be absolute value of x in the numerator divided by n plus 1. So as I take the limit, as n goes to infinity, what do I get? What's that?
0.
0, yeah. Equals 0. So the question is, does the convergence here depend upon the choice in x? If I chose some value for x, would it still converge to 0?
All x's.
It's true for all x's, right? And no matter what x I plug in here, the limit of this sequence will always be 0. So what does that imply about our ROC? Our ROC is all real numbers. There are no x's for which this thing doesn't converge. So, I can say there's different ways of saying it. We could say it's, negative infinity to positive infinity in interval notation. We can say x, any x in the real numbers, different ways of putting it. You could just say r, whatever. Some way you indicate that it's everything. So that's pretty interesting. This thing converges for all x's. If we look back at the series, maybe that's not so surprising because we've got a factorial in the denominator and we have an exponential in the numerator. And one thing that we've learned as we're starting to get in a feel, get an intuition for these things, we know the factorial grows really stinking fast, much faster indeed than an exponential. So no matter what I put in there, this thing will always outgrow it, which means this thing will always converge. That's at least the vibe. It's not a rigorous argument, but it's one way of looking at it. So this shouldn't be necessarily surprising if we think about what we already know about series. Another way to think about these power series is that they are really a family of series. Since we generate a new series for every choice in X, right? This expression gives me a bunch of different possible series, right? And what we're doing here is finding out for what choices in X will I generate an actual convergent series. But the way to think about this expression is not as a series unto itself, but as a family of possible series, where each member of the family corresponds to a particular choice in X. So far, you've just been looking at individual members of different families. Now you're looking at the whole family of series. Let's see how much time we got. Okay, good. All right. Last example. Now we're looking at the series from 0 to infinity of n factorial times x to the n. So before we even start writing stuff down, does anyone want to wager a guess what happens with this guy? Remember, the thoughts that you should be thinking are, for what choices in X can I render this convergent? And if you think of each choice in X as generating some new series, right? Some series that you've seen before, or potentially you've seen before. What would you think about any one of those series? Use your gut. What do you think?
I mean, somewhat looks like a geometric, but I mean, I feel like that's kind of the whole thing with it, so that's not special.
Yep. And we know it's not a geometric because our
Yeah.
coefficients here, right, are not constant. So think about this. One of the members of this family, right? This is a family of series. One of the members of that family is when I choose 1 for X. So if I look at X equals 1, I get this. What do we think about that series? Definitely divergent, right? This thing blows up. All right. So we saw that for one choice in X, it was divergent. Suppose I chose another X equals 2. Then I would have the series n factorial times 2 to the n. What do we think about that?
Divergence.
Divergent, right? I mean, now it's a product of a factorial and an exponential. Both of these things grow really fast, If I multiply them, they grow even faster. So this thing is going to blow up. So yet again, it's divergent. Right? So once you start, here we're turning the dial, right? We started at 1, then we clicked it over to 2. Both of those choices generated a divergent series. So what's our expectation for this guy?
Full divergence.
Total divergence. Total divergence. Well, let's see. Which would mean what for the radius of convergence?
No X values which satisfy it.
Say that louder.
There are no X values which satisfy it.
So what if you write that down as an interval, what's that going to be? Nothing, right? There is no interval. It's empty. So we'd expect maybe that there are no x's for which this is convergent. Well, let's see. Let's look at the ratio test yet again. N plus 1 factorial, x to the n plus 1 over n factorial, x to the n, absolute values. This will simplify to n plus 1 times the absolute value of x. And n plus 1, as n goes to infinity, is going to go to infinity, right? Except in one case. So it equals infinity, or what? Is there any choice in x for which I could render this convergent?
Zero.
Yeah, 0.
0, right?
0.
And if I choose 0, then the whole thing will converge to 0. So it goes to infinity if x doesn't equal 0 and equals 0 if x equals 0. So radius of convergence, what is it going to look like? For what choice of x do we get a convergent series?
That's
What?
just 0.
Just 0, right? So how do we represent that? There's a couple different ways to do that. It's going to be, we could say the radius of convergence is just 0, right? Or we might be able to say it that it's divergent. This is sort of, roughly equivalent. It's divergent for any x in the real numbers minus 0. Now that's another way of saying it. It's a little bit more mathy, but they both amount to the same thing. So the radius convergence is just a single point. So we've kind of seen the full spectrum of possibilities here. And I'll state this as a theorem that your radius of convergence could be a finite interval that could include or not include or exclude the endpoints. That's, so we saw all the possibilities there. It could exclude both. It could include one. It could include both. Or it could be all of the real numbers, or it could be only one number, right? But the one thing that we don't see is that there is no choice in x for which you'll get convergence. Because generally, if you have a power series centered at A, it will always converge at A, at the value A. So since this is centered at 0, it converges at 0. If it was x minus A, we'd see that it converges at A. So we always have at least one point for which we have convergence. And that's what we saw. So we'll pick up with this next time. It'll be a bunch of theorems, but it'll all pretty much summarize this stuff. So I'll see you guys tomorrow.
Wait, we do not have
Tomorrow.
tomorrow.
Wait, no, not tomorrow, Wednesday.
Yeah.
Oh,
Thursday.
Wednesday. Yes, I'll see you Wednesday.
Just
No, Thursday.
Wait, guys, what?
If you all think you do.
Let's make this 5 right now.
No,
Looking to move on that.
Oh, yeah.
That's, yeah, in person.
And if you haven't turned your quiz into Nick, then you're SOL, right? So that the window of application is closed for that.
Yeah, I like to, because I know how to do it.
It's a lot more.
If y'all want to do Calc 2 tomorrow, though, you're still welcome to do Calc 2.
Really?
All right, Murphy, that's.